Swayam Prabha. Digital India. Educated India.
Hello everyone. We'll continue our discussions on discrete distributions today. If you remember, in our previous discussion, we looked into normal distribution and exponential distribution. And now we are going to cover two very important distributions, binomial and Poisson distributions, when we talk about discrete distributions. And then we'll go to a few examples where we will look into how to account for discrete events while quantifying risks for different kind of events. And finally, we'll conclude this discussion by looking into combined examples where both discrete and continuous distributions come into play. The first distribution of our interest whenever we talk about discrete distribution is a simple but very effective and widely used binomial distribution. But before we understand details about binomial distribution, let us talk about Bernoulli trial, around which these concept of binomial distributions are built. So when we talk about Bernoulli trial can only have two outputs or two possible outcomes, that is success or failure. For example, in coin toss, we have heads or tails. In a coin toss, if we call for tail, we can say that if tail happens, it is success. And the other event, of course, would be failure if we have called for tails. So that's a classic example of Bernoulli's trial. In the context of hazard, we can, of course, deal with magnitudes of hazard as continuous variables. For example, level of flood can be 5.5 feet, 5.6 feet, and so on. But we can also use binary classification, that is whether a particular event is extreme or not. So answer can be yes or no. And whenever we can come up with this binary answer, that is success or failure, extreme yes or no, we can typically model these particular events as Bernoulli trial, assuming that events are IIDs, that is independent and identically distributed. What does that mean? That output of previous event does not influence outcome of next event. Again, if we go back to our coin toss example, if our coin is fair, doesn't matter how many times we get head, next time getting tails still would have probability of 1/2, because these particular events are independent and identically distributed. Now, whenever we talk about Bernoulli's trial, we denote or represent success by P and failure by 1 minus P. And for brevity, we sometimes write it as Q. So Q is equal to 1 minus P, because either it is success or it is failure, and because only two possible outcomes are there. Now, when we talk about binomial distribution models number of successes in fixed number of Bernoulli trial. And that is why it is important to know Bernoulli trial before we talk about binomial distribution. Mathematically, we can write the expression for binomial distribution as, where x is our random variable, that x, probability x taking value of k, is equal to n choose k, p raised to power k, 1 minus p, and or this 1 minus p is also q raised to power n minus k. In this case, n is the number of trials. For example, if I'm tossing a coin 10 times, in that case, n would be equal to 10. K is the number of successes. Let us say I want to get exactly three heads. during this coin toss experiment, then K would be equal to 3. P is probability of success. In case of coin toss, P is equal to 0.5, and Q of course would be 0.5 because it is also 1 minus P in this case, and NCK is a typical binomial coefficient which accounts for the fact that this success can come at any possibility. So when we say that 5 successes, that we are essentially implying that 10 choose 5, and that's where these combinatorics take care of it. Let us try to understand application of binomial distribution using our flood example. Let us consider a flood in a given year can be modeled as a Bernoulli trial, where P is the probability of flood occurring in a year, and we assume some value based on some data analysis that P is equal to 0.3, or there is a 30% chance of a flood occurring in a particular year. We are interested to model this particular flood over 5 years of time, and hence in this case N becomes 5 and P becomes 0.3 and Q becomes 0.7. Again, we have to keep on reiterating that P plus Q is equal to 1, so we did not specify P and Q separately. Now, when we talk about probability of exactly K floods in 5 years, we can simply say 5 choose K, 0.3 raised to power K, and 0.7 raised to power 5 minus K. And we can now plug in different values of K and calculate probabilities of X taking that particular value. For example, I have done a small example for you in our next slide where we did probability of X equal to 0. That is no flood in any of these 5 years. We simply say 5 choose 0, and this number would be 1. 0.3 raised to power 0. Again, it would be 1, and 0.7 raised to power 5 comes out to be 0.168, or there is 16.8% chance that we will not get any flood in 5 years of period. Now, I have left next 2 exercises for you where I have asked you to calculate probability of exactly 1 flood in 5 years and 2 floods in 5 years. I will just write that particular expression for you, that if I have to write probability of X equal to 1, I can do 5 choose 1, 0.3 raised to power 1, and 0.7 raised to power 5 minus 1, which is equal to 4. And I can definitely write this 5 choose 1 as 5 factorial divided by 1 factorial into 4 factorial into 0.3 into 0.7 raised to power 4. And when we solve it, we get probability of exactly 1 flood in 5 years. And similarly, you can keep on changing value of K, that is X equal to 1, 2, 3, 4 and 5 to get the probabilities of K number of floods in N years. Now, this was a very simple example where we were talking about exactly these many events over a period of interest. We can ask even more interesting questions that would be very useful while quantifying risk in our decision-making exercise, is that we can ask a simple question: what is probability of exactly 5 floods in 5 years? And this analysis would be very similar to what we did before. That is 5 choose 5, 0.3 raised to power 5, 0.7 raised to power 0, and we should get our answer of probability of exactly 5 floods in 5 years. But more interesting questions can be: what is probability of at least 2 floods in 5 years? What is the probability of at most 2 floods in 5 years? So first of all, before we go to the math of it, let us try to see what we mean. This particular case is pretty straightforward. That is probability of exactly 5 floods. We are essentially saying X equal to 5. It becomes 5 choose 5, 0.3 raised to power 5 and 0.7 raised to power 0. We simplify it, and whatever answer we get is our probability of X equal to 5. Coming to, I would not say it's very difficult, but still we have to exhaustively account for our sample space, that what we mean by probability of at least 2 floods. At least 2 flood means what is probability that 2 flood happen, or 3 floods happen, or 4 floods happen, or 5 floods happen. Whenever we use word or, as we discussed in our previous lecture when we were talking about some basic fundamental mathematics of probability and statistics, we learned that this OR would be additive probability, assuming that all these events are independent of each other. In separate years, the probability of flood in third year is not influenced by second year, and it is also not influencing probability of flood in next year, and that's what constitutes IIDs, and hence we can simply summate them together. So now it again becomes a very simple problem, that all we have to do is 5 choose 2, 0.3 raised to power 2, 0.7 raised to power 3. For x equal to 3, we can write 5 choose 3, 0.3 raised to power 3, 0.7 raised to power 2, and so on. Two more terms will come for x equal to 4 and x equal to 5. That is going to be our probability of at least 2 floods in 5 years. We can also think of it as 1 minus probability of 0 floods and 1 flood, because sum total of probabilities is always equal to 1. So either 0 floods can happen, 1, 2, 3, 4, 5 floods can happen, and hence we can go either way. This will become clearer when we talk about probability of at most 2 floods in 5 years. What we are looking into, probability of at most 2 floods would be that x, either 0 floods happen, or 1 flood happen, or 2 floods happen. So again, this becomes sum on the other side. So if we add at most 2 floods and at least 1 flood, we are going to get 1. So you determine any of them, subtract it from 1, you are going to get to your desired answer. So now if this is clearer, let us look into a sibling distribution of binomial distribution, what we call as the geometric distribution. In binomial distribution, we were interested into probability of n number of successes. But in geometric distribution, we are interested into the probability that success will happen at a specific trial. That is, I am tossing a coin. I am tossing a coin 10 times. I can always now easily answer a question, what is the probability of getting head 5 times? What is probability of getting head 6 times, and so on. But now I want to determine that what is the probability that my first success, if head is success, it would happen at 3rd time or 4th time or 5th time. That is, rather than the number of heads, I am interested in the time instant when the particular event is realized. So in that particular case, I use geometric distribution, which essentially is that probability that k is the trial on which first success occurs, and probability of x equal to k now becomes 1 minus p, k minus 1 multiplied by p. What this formula is essentially telling us, that we have to get failure in first k minus 1 trials, because we want our first success to happen at kth trial. And how that can happen? If first k minus 1 trials are failure and kth trial is success, only then we can say that my first success came at kth trial. And that is why this 1 minus p raised to power k minus 1. So q comes first, and then this accounts for success. P accounts for success at kth trial. This particular concept of geometric distribution is very, very important for defining return values. We'll come to that later. But before we go there, let us look into a very simple example to reinforce this concept, that how geometric distribution is typically used. Now, let us consider a new flood event in a given year with probability p is equal to 0.2. We want to find the probability that first flood occurs in the 3rd year. Now, it's pretty simple now based on the maths that we have already learned, that we will simply say probability of x equal to 3. No floods in first 2 years. That means q raised to power 2 multiplied by flood in 3rd year, that is p. So it simply becomes 1 minus p, which is 0.8 square into 0.2, and it gives us the value of 0.128. So the probability that first flood occurs in 3rd year comes out to be 12.8%. Now, as I said, that with this particular foundation, we are good to go and talk about return level concept. Return level, by the way, is used in civil engineering whenever we talk about design of hydraulic structures or design of structures that are exposed to winds, because we are designing our infrastructure for, let us say, 50 years or 100 years. So we cannot design our infrastructure facilities for mean traffic, because that would mean that it would fail perhaps 2 times in a day if mean traffic is exceeded. Hence, most of these infrastructure or structural facilities are designed for rare events. And while rare is a qualitative word, quantitatively, civil engineers typically use this language of return period, that what is the average or estimated time lapse between two consecutive events of a particular magnitude. So when we talk about a return level of 1 year, that means it is expected that this particular event will happen every year. When we talk about return level of 2 years, it is expected that this particular event on an average will happen once every 2 years. Again, we are talking about it in probabilistic sense. One mistake civil engineers and sometimes decision makers also do, they think that, if a 100-year return level event has happened this year, it will definitely happen after 100 years. That is not correct. Why? Because it is in probabilistic sense. It may happen next year also, and then it may also happen over third year, and that may call for reassessment of return level periods if it is continuously happening again and again and again. But statistically speaking, a return level event, even if it happens back to back, would not alter it to a 1 year return level event, because these numbers are statistically estimated based on the data that we curate over long period of time. And hence it is important to inquire into how mathematically return levels are defined, so that we don't do this mistake that if return level happens now, it may not happen again in next year. So return level is the mean recurrence rate, which is expected value of t, ET. We already learned how to model at what particular event t is going to happen. That means we now know probability distribution of t, which is 1 minus p raised to power t minus 1 into p, because that's what we learned in geometric distribution. If we talk about expectation of any function, egx, we learned that for a discrete distribution, we can simply sum it over its entire domain. And typically we say that sum over all t equal to 0 to infinity, because time cannot be negative in this particular instant. So we will still go from minus infinity to infinity, but function doesn't exist from minus infinity to 0, because time cannot be negative. Hence, we go from t equal to 0 to infinity, gx multiplied by probability distribution px. Now, in this case, we are interested in expected value of t, that is gx itself is t. So we will still summate over t equal to 0 to infinity. Gx becomes t, and px is 1 minus p raised to power t minus 1 into p. So expected value becomes this mathematical function which has element of p and of course x itself. So it does not defeat our fundamental definition of expectation that we learned earlier in fundamentals of mathematics. Now, I would not worry about mathematics here, but for sake of completeness, I have expanded all these particular forms. That is what expected value of t, and when I sum over all individual points, it essentially becomes a form of geometric progression. And I am not surprised, because we are expanding a geometric distribution over its entire domain. So geometric progression is not a surprise that why it becomes a GP, because that's how the mathematics of geometric distribution is anyways written. Hence, when we expand it, and apply some basic mathematical operations, which again I would not worry about at this stage, but if you are interested, you can pause the video and look here. We essentially look into that our expected value of t, s, becomes 1 into 1 minus q square, and when I reintroduce this s, this particular term, that is 1 into q, 2q plus 3q square, is what we termed as s in this mathematics. Expected value of t becomes p into 1 minus q square, and we know that 1 minus q is p. So this becomes p into 1 upon p square is equal to 1 by p. That means that estimate of return level is the probability, or 1 by p itself. That is, if I say that I am having a coin that I will toss only once in a year, what is the expected return level when I will get heads? So it essentially is probability of getting head in one particular trial is 1 by 2. So every 2 years I can expect to get or roll heads in a coin toss, and hence a return level of heads becomes 2 years if I am tossing my coin once in a year. Now, when we talk about floods, same thing happens. Now we have related it to probability of success. If probability of an extreme flood is 0.2, that essentially means that return level of that particular flood is 5 years. And that's how we can now relate the probabilistic language to engineering language of return levels. Now, return level, as we discussed, is period of time between occurrences of certain event, such as flood exceeding a specific level. Another related concept that we use is called as probability of exceedance. Probability of exceedance is defined as that probability that an event will exceed within a specific time period. Now we already related this 1 by t to p, that 1 by t is equal to p. So we are simply looking at that particular magnitude of x that is going to equate to p, and p is nothing but 1 by t. So we can now go from return period to return level by using this definition of probability of exceedance. That is, if we are talking about return level of a 100-year event, we are essentially saying that what would be the value of x, that would, the small x, that would satisfy this particular equation. And if we know the functional form of probability of x greater than equal to x, be it in continuous distribution, be it in discrete distribution, we have solved similar kind of examples where we determined probability of x greater than equal to x and determined what should be value of x using inverse and so on. And hence we have solved this particular problem of going from return levels to return periods. Now this brings us to next distribution under discussion, which is Poisson distribution. Now Poisson distribution says that what is the probability of having k number of successes, and here we are not essentially looking into success or failure. Here we want to cover discrete number of events. For example, if I want to model number of floods in given year, or number of earthquakes exceeding certain magnitude, let us say Richter scale 6 in given year, or I am interested in number of floods in 30 years. If my infrastructure is designed for 30 years, I may not be interested in year by year calculations, but I want to look into long-term horizon, that is how many floods I can expect in 30 years and so on. Now, if you see that difference between binomial distribution and Poisson distribution is that in binomial distribution, we were just concerned about success or failure as an outcome. So there were only two possibilities. Now we are interested into number of events that can happen. This can be 1, 2, 3, 4, 5, 6, all the way till infinity. Hence, it is a discrete distribution that does not take only two possible values, and we typically use Poisson distribution after ensuring that goodness of fit tells us that our samples are indeed coming from Poisson distribution. And mathematical form of Poisson distribution is again exponential decay. Now, one unifying thread across all our distributions so far, and we can also show that the limiting case of binomial distribution also assumes the case of an exponential decay. But when we talked about normal distribution, exponential distribution, and now Poisson distribution, all of them are some exponential function of parameters. In this case, this takes the value lambda to the power k, e to the power minus lambda, and k factorial. I deliberately used parameter lambda here because in exponential distribution we also use lambda, but this particular lambda is different than what we use for exponential distribution. Sometimes when we are reading few textbooks on probability and statistics, they also tend to use similar notation, and we assume that the lambda values would be same whatever we use in exponential distribution, and hence use it in Poisson distribution, but that is not correct. In this case, lambda is the average rate, that is mean number of occurrences that are happening every and k is the number of occurrences. And this is where it differs. For example, if my average rate of flood is 1.5 floods per year, and I am interested to look into number of floods for 50 years, in that case, my lambda will take the value of 1.5 times 50. So, over the design period, multiplied by what is the mean number of occurrences in a given time period, multiplied by total time under consideration. And that is a subtle difference between lambda that we use in Poisson distribution versus what we have used in the exponential distribution, which happens to be a continuous distribution. And of course, k factorial would take the value of whatever is the point of interest in terms of number of variables that we are looking for. Let us look into an example. That is, mean number of floods each year is 1.5. We have to calculate probability that number of floods will exceed 2 in next 2 years, and probability that number of floods will exceed 5 in next 2 years. So let us look into this particular example. In first case, we are interested into number of floods will exceed 2 in 2 years. So lambda becomes 1.5 into 2 equal to 3. We are interested in probability of x greater than 2, which is simply 1 minus probability of x less than equal to 2, because probability of x greater than 2 plus probability of x less than equal to 2 is equal to 1. So rather than going sum from 2 to infinity, let us get with 0, 1, 2 and subtract it from the overall maximum probability possible, which is equal to 1. So we get probability of x less than equal to 2 as probability that x equal to 0, x equal to 1 or x equal to 2. So when we again look into this general form, we are looking into lambda to the power k e raised to power minus lambda upon k factorial, where lambda takes the value equal to 3. So probability of x equal to 0 comes out to be 4.98%, x equal to 1 comes out to be 14.9%, and x equal to 2 comes out to be 22.4%. I'm just reading these decimals in percentage form for ease of notation. So probability of x less than equal to 2, that is, we will get less than 2 floods in 2 years, come out to be 42%, and hence probability we will get more than 2 floods come out to be 1 minus 42%, which is approximately 57.6%. So that's a very simple example that how we can really put distributions to use to calculate number of events that we can expect when number of events are discrete. Similarly, you can look into next example, that what is the probability of more than 5 floods in 2 years. Again, period of study remains 2, so lambda will be 1.5 into 2 equal to 3. Again, probability of x greater than 5 simply can be 1 minus probability of x less than equal to 5. So 0, 1, 2, 3, 4, 5. Sum of all of these subtracted from 1, we have our answer. In this case, it comes out to be 8.4%. If you see that probability of x greater than 2 was 57%. Probability of x greater than equal to 5 in the same period is 8%. And this is what exponential distributions do. There is no linear way to reach from x equal to 2 to 5 because the decay is much, much faster than we expected. When we go to probability of x equal to 8, 9, 10, values would tend to 0 or almost non-existent. And that is why these distributions are also called as thin-tailed distributions. That is, probability of finding values away from the mean is close to 0, far away from the mean. Probability of x equal to k becomes non-existent when k is far, far away from the mean. And that is why these thin-tailed distributions, while important, are seldom used to model extreme values of interest. But again, these are the building blocks of those extreme value distribution. But for sake of completeness, I had to mention that even if we are tempted to do so, we have to be very, very careful with choice of distribution, even if its maths is a bit easier. So let us look into this example where we try to bring in the concepts learned for discrete as well as continuous distribution to solve a real world example on risk and insurance calculations. So let's begin with a bit of a simpler example and then we'll add layers to that. So this problem says that there is a structure. Let us consider a transmission tower which is located in a region where cyclone wind force must be considered in its design. From records of cyclone for past 20 years, the mean occurrence rate of cyclones is once in every 10 years. So we know that mu in this case is 1 by 10. So the occurrence of these cyclones can be modeled as Poisson distribution. This information is important because now we know the functional form of our random variable that it would follow when we will look into the modeling the probabilities of x greater than equal to k and so on. And it is given that structure is designed to withstand a cyclone force with an allowable probability of damage of 20%. That is, whenever a cyclone of that particular magnitude will hit, it will not get damaged. Its probability is also 80%. We have to answer the question that what is the probability that this structure will be damaged in next 50 years. Now, again, there are two factors into consideration. Given that a cyclone happens, damage probability is 20%. So if one cyclone happens, then there is 20% chance that it will be damaged. If two cyclone happens, then of course chances that it would be damaged keeps on increasing and so on. But we have uncertainty around how many cyclones are going to strike. Before we put that number of cyclones into consideration, let us calculate all the things that are easy to do first. First of all, we will calculate lambda. Here, period of interest is given to be 50 years. So we will calculate lambda as 0.1 multiplied by 50 because 0.1 was mean occurrence rate. 50 years is the time period for which this particular system is designed. So this comes out to be 5. We further know that probability of damage in each cyclone is 20% and hence probability of no damage in each cyclone is 80%. Now, if we combine these two, that if n number of cyclones happen, probability of damage becomes 0.8 or probability of of let us go back here, because to go towards probability of damage, we can follow an easier route, that sum of probability of damage and probability of no damage is equal to 1. So there are multiple ways for a particular structure to get damaged. That means it may get damaged in event 1 or event 2 or event 3. Also, it may get damaged in event 1 as well as in event 2. So if we go from probability of damage side, we may have to look into large number of possibilities or permutations and combinations. However, there is only one way for infrastructure not to get damaged, is that it is not damaged in first cyclone, and it is not damaged in second cyclone, and it is not damaged in third cyclone. Whenever I am overstressing the use of or and, I am essentially talking about summation and multiplication. So when we deal about probability of no damages, we are dealing with no damage in this and second event and third event and so on, which would make mathematics much more tractable, as number of combinations to deal with are minimal. That is, if one cyclone happens, no damage should happen, and chances of that is 0.8. If two cyclone happens, no damage should happen in both of them. That is 0.8 multiplied by 0.8 multiplied by probability of two cyclones happening. If n number of cyclones happen, no damage should happen in n number of cyclones. That is 0.8 raised to power n into probability of n number of cyclones. So this 0.8 raised to power n comes from the fragility characteristic of that particular tower under consideration, and probability of n number of cyclones happening come from the Poisson distribution assumption that is already specified in our conditions. Now, we also don't know that how many cyclones will happen. So number of cyclones can be 0 or 1 or 2 all the way to infinity. Hence, the mathematical form can be written as that probability of no damage is equal to sum from n equal to 0 to infinity, 0.8 raised to power n, lambda to the power n, we already specified value of lambda as 5, upon n factorial into e to the power minus 5. We can also write this particular expression as 0.8 multiplied by 5 in bracket raised to power n, e to the power minus 5 is constant, divided by n factorial, and this particular term is summed from n equal to 0 to infinity. And that is where other related concepts of mathematics comes into picture. If you may recall that expansion of e to the power x is also given into some form of factorial as x to the power n upon n factorial, and all the sums from n equal to 0 to infinity. And this particular expansion in mathematics is called as Maclaurin series expansion. I'll not go into details here, but I strongly recommend to refer to a book on mathematics to look into that, what is this standard Taylor and Maclaurin expansion. But what is important here is that rather than dealing with these factorial till infinite terms, we essentially have much simpler representation of this particular summation as e to the power x. In this case, x takes the value of 0.8 into 5, which is essentially 4, and hence we are looking at e to the power 4 multiplied by e to the power minus 5. As simple as that. So just going through the complex mathematics and clubbing the terms in logical way, we essentially get probability of no damage as 36.79%. We were interested in probability of damage. So probability of damage comes out to be 1 minus 0.36, something of the order of 64%. 66.6321 is the exact value. That is, there is 63.21% chances that this particular infrastructure will get damaged during cyclone in next 50 years. Now this is problematic. 63.21% is too high of a probability for an infrastructure system to fail. Where is the problem? Problem is that we were allowing infrastructure or a particular structural system to fail with probability of 20% in each cyclone. And hence, when summed from 0 to infinity, this 20% failure keeps on manifesting itself and gives us the total probability of range of 63.21%. And we can say that this particular structure is too fragile to be designed in a zone with high cyclonic activities, because their number of cyclones can be on fairly larger side, and here anyways we are getting 1.5 cyclones per year, so probability of failure will definitely be closer, it would be on much higher side, even higher than the 20%, that is the probability of failure in a particular event. So what we should do? We have to take a decision. And here we decided that we will upgrade the structural system and reduce the 50-year probability of damage to 5%. So now we know that probability of damage should be 0.05 or probability of no damage should be 0.95, and this is where our codal provisions, IS codes, come into picture that tell us what is the tolerable risk that we are going to deal with. Here we say that we cannot make a bridge or a transmission tower out of titanium because of cost issues. So we cannot ensure that there is a 100% guarantee that particular infrastructure system will survive a cyclone. So we will still take a risk, and we will say that now in 5% cases this can reduce from 63%. We are reducing our probability of damages directly to 5%, and that means that structural strengthening or use of alternate materials is needed to be compliant to this particular standard. Now the question is, what should be the allowable damage probability against a cyclone wind to achieve this target? So now the question is very much similar, that rather than finding probability of non-damage, we are already given that particular value. But what was known as 20% in last example is not known to us. So we don't know what is probability of failure, which was 20% last time. In this case, it becomes a question mark that we have to determine. And probability of no failure, of course, is also not known to us. And that is the only parameter that is unknown in this entire scheme of things. Lambda still remains the same. It's the same location, same site, same design period. So lambda still takes the value of 5. And mathematically, we can write this as probability of non-damage now becomes 1 minus p raised to power n. If you remember, earlier we were saying 0.8 raised to power n, but now 0.2 is not known. Hence 0.8 is also not known to us. So 1 minus p raised to power n, lambda to the power n, lambda is equal to 5. E to the power minus lambda upon n factorial. Again, this simplifies to, this again form our Maclaurin expansion of e to the power x, and when we simplify, we simply end up with e raised to power minus 5p is equal to 0.95. Taking anti-log on both sides, we get our answer as 0.01 or 1%. So we have to reduce our infrastructure fragility from 20% to 1% to ensure that over 50-year period, we have reliability of 95%. Now, if you think it and put this particular concept into perspective, right from the distribution, we have taken a big leap to make a decision. We have converted our maths into something tangible to engineers that engineers can use to augment their design and infrastructure installation capacities, because these 95% and 1%, they are not directly related. They are related through series of mathematical operations that we achieved through this use of probability distribution and knowledge of what is the fragility of individual infrastructure system. And that is exactly where decision making and probability go hand in hand, as lot of things in real world are uncertain, and probability distributions help us understand or quantify that uncertainty in best possible manner. Now, keeping our ritual intact, we should conclude this particular discussion also using example from flood, and I have tried to make this example even more interesting by relating it to an insurance world. As many of you are familiar with this insurance, that is, let us say you have an expensive asset, it could be your car or your home. If it is subject to different kind of hazards, you may be at risk of losing that entire value. So if you have a car that costs 20 lakh rupees and it is running on the road, it may be subject to man-made events, like you may enter into accident with another car or any other structure or tree, for example. Or there can be a natural calamity. There may be flood in a particular area, your car is parked there, water enters into your car, and it may end up damaging an expensive asset which may have a market value of 20 lakh or something. So what you do every year, you look into that what is the value of that particular asset. Since car is a depreciating asset, every year you say that I bought this car for 20 lakh, next year it may be 19 lakh, 18 lakh, 17 lakh and so on. And then you go to an insurer and tell them that I want to get my car covered for personal third party covers, as well as get some natural event protection. And they will tell you that to protect a car of this particular value, which is located in this particular area, you may have to pay a particular amount. And this amount is typically 1% to 1.5% to 2% of the total asset value. And interestingly, now your driving habits may also be accounted for to give you incentives or quote unquote punishments on the insurance premium. But in this entire process of going from a car that is parked into your garage to your insurance premium, these corporations are essentially trying to manage the risk. They are buying out your risk from you at cost of certain premium, because probability of things going wrong may impact you in entirety, but you don't want to pay out that particular amount from your pocket, and hence you go for sharing that particular risk with other policy holders, because probability that things will go wrong for all of the people who are buying into that particular insurance is very close to zero. So this determination of insurance in a nutshell is a probabilistic exercise, both for you as well as for an insuring company. So here is another example that put this particular discussion from car into a civil engineering context, that how large scale flood extents can be insured or their premium can be decided. So in last 50 years, in a particular region, there were two large floods. These large magnitude floods are modeled as Bernoulli's sequence. For sake of uniformity, I should use word extent in place of magnitude here. So we are talking about large extent floods that may cover a few square kilometers in a particular region. When large scale flood happens, when these large extent flood happens, their depth is normally distributed with mean depth of 5 feet and coefficient of variance is 0.25. Coefficient of variance essentially relates mean and variance. So if we know coefficient of variance and mean, we can easily determine standard deviation and hence variance. Also, it is given that infrastructure in the city will face damage if water depth exceeds 6 feet in these large extent floods. See, extent does not talk about depth. So there are two parameters. X, Y is the spatial extent, and depth, how much water will stand vertically that may enter into infrastructure systems, is another parameter that we are more interested in here whenever these large extent flood happens, we have to calculate the probability that infrastructure in city will face damage due to these large extent floods. Further, we are asked that if infrastructure cost having high vulnerability to flood in this particular region is $1 billion, what is a defensible insurance premium that a city can pay per year to be insured against these particular floods? Why the word defensible comes here? Because ultimately in most of the setting it's going to be taxpayers' money. So if we pay out huge premiums and that particular damage is not realized, then insurance premium then taxpayers may question the government that why our money is being used for something that is not even happening. Hence, there has to be a defensible, mathematically defensible reasoning to decide that particular premium. So let us look into the mathematical treatment of this particular question. So we are given that mean depth is equal to 5 feet, coefficient of variance is 0.25, and coefficient of variance is equal to sigma per unit mean. We introduced that in one of our earlier lectures. That means sigma comes out to be CV, which is 0.25, mean is equal to 5, which is 1.25 feet. It is given that infrastructure systems will be under stress only when depth of flood exceeds 6 feet, and depth of flood is normally distributed. That means we should convert this 6 feet into our standard normal variable by subtracting mean and dividing by standard deviation. So we get our z value or z value as 0.8. Now when depth of flood is less than 6 feet, there is no problem because there is no damage. So we are interested in what is probability that x is greater than 6 or equivalently z is greater than 0.8, because x greater than 6 corresponds to z greater than 0.8 from the z transformation that we just did. And using the standard normal distribution table, we can focus on z equal to 0.8 and see the value is around 7.881. So probability of z greater than 0.8 is 1 minus 0.7881, because table gives us value of probability of z less than equal to 0.8. So if we subtract that from 1, we get probability of z greater than 0.8 as 0.21 or 21.19%. So that is the probability that depth of water during a large scale flood will exceed this particular mark. Now, we don't know how many large extent floods will actually happen. There can be 0, 1, 2, 3, 4, 5, 6 again, and whenever they will happen, probability of having a damaging level is 21%. So this 21% now has to be brought together with total number of flood events, which again becomes similar to the problem that we did earlier. The probability of flood level exceeding 6 feet, given that large scale flood happens, comes out to be 0.2119. Hence, probability that there would be damage given that there is large extent flood is equal to 0.2119, and probability that there is no damage given that there is large extent flood, writing it as LEF, is equal to 1 minus 0.2119, which is equal to 0.7881. So in a given year, if we have to calculate probability of damage, we again go the same route, that is 1 minus probability of no damage. And how no damage can occur? That if one flood happens, no damage happens, and two flood happen, no damage happens in both of them. So again it becomes summation from n equal to 0 to infinity, 0.7881 raised to power n, 0.04 raised to power n, because in this case our lambda comes out to be 2 by 50, which is equal to 0.04, as two large extent floods happened over 50 years. So 2 by 50 becomes 0.04, and we are deciding annual insurance premium. So we will just multiply this 0.04 by 1 because it's 1 year under consideration. If we would have been talking about 50 years, we would have multiplied this number by 50 because that's what we learned in Poisson parameterization, that lambda is equal to mean occurrence rate per unit time over time into consideration. And here, since it is 1 year under consideration, lambda is essentially equal to 2 divided by 50 without any other multiplication of time period. And again, this takes the form of Euler and Maclaurin expansion of e to the power x. So we simplify this and we get probability of no damage comes out to be 0.9916, or probability of damage comes out to be 1 minus 0.9916, which is 0.0084. That means there is only 0.84% chance that our infrastructure is at risk in a given year. Now, this number looks very small and we may tend to ignore that. So our first intuition should be, okay, let's not get an insurance for that. But now if we multiply it with the total asset value that is exposed, it's an order of $1 billion. So a large exposure, even multiplied with the smaller probability, may result in disproportionate losses. So when we multiply this probability of failure with the asset value exposed, we get an answer of around $8.4 million. And hence, a defensible insurance premium that can be paid for this particular investment comes out to be of order of $8.4 million, because our infrastructure that was at risk of $1 billion, and even a low probability event of higher risk, low probability event when multiplied with high asset value gives us a much higher value of risk. Now we have again used two concepts that we learned in our prior classes around Poisson distribution and normal distribution to convert it to a decision making for real world, whether to buy an insurance or not. And answer is in front of us, which is quantified, which is logically derived, and despite all the assumptions that go into that, gives us the best possible framework to act upon. So some assumptions that we indeed made in this particular case is that our flood events are independent. That is, if next event is happening, it is not being influenced by second one. But those who are familiar with hydraulics and hydrology, they would know that two flood events that are happening in close proximity may not be essentially independent because of various conditions, including antecedent soil conditions and so on. We assume that annual occurrence rate is constant, but we have been talking about climate change throughout the globe, right? And hence it may happen that the probabilities or the parameters that we are using in these probabilities, they themselves may change. So we are modeling all these processes under assumption of stationarity. And hence, when these assumptions are relaxed, we may be looking into variability in estimates of probability as well as the annual occurrence rate of these particular events. But it is important for us as an engineers and scientists to state an assumption while ensuring that we are using best mathematical information and framework to get answers to our problems. Thank you.